Okay. Should I start now? Okay. Hello, everyone. My name is Jiayue Yang. I'm a second-year master student from Roman and Liège's research group, and I'm from Waterloo and the Perimeter Institute. Today, I would like to talk about the dynamic behaviors of black hole phase transitions near quadruple points. And this presentation is based on this paper. First, I will give you an introduction on the black hole thermodynamics, and then we will talk about the quadruple points in black hole phase transitions. Next, we will study the dynamic processes at the quadruple points, and also the first passage events. Finally, I will make a conclusion. So first, what are black holes? In 1783, John Michell realized that the gravity of star could be strong enough so that the escape velocity of the star may be bigger than the speed of light, and he named the star the dark star. And this is the first motivation of the black hole. And then in 1915, Albert Einstein proposed the general theory of relativity, and the next year Schwarzschild obtained an exact solution of the Einstein field equations. And so now we have the exact definition of the black hole. Black hole is a space-time region that has a strong gravity that nothing can escape. So the point of no return is called the event horizon. And now, today we know that black hole actually exists. In 2002, Gano found the first indication that black hole may exist. They found there exists a supermassive black hole at the center of our Milky Way, and this is a reference. And in 2015, the LIGO collaboration first detected the gravitational waves of the merger of two black holes. And more recently, 4 years ago, the Event Horizon Telescope collaboration took the first ever image of the black hole, which lies at the center of the galaxy. And this is a picture of the black hole. So today we know that the black holes actually exist. So this is a very brief introduction on black holes. And then we will talk more about the black hole thermodynamics. So the next part is from black hole thermodynamics to the black hole chemistry. And the next few slides are based on this paper, Black Hole Chemistry, Thermodynamics with Lambda. So what is black hole thermodynamics? In 1970s, Bardeen, Carter, and Hawking proposed the 4 laws of black hole thermodynamics. The zeroth law is that the surface gravity kappa is constant over the event horizon of a stationary black hole, and the surface gravity kappa here will be interpreted as Hawking temperature later. And the first law is for a general black hole that has a mass m, an angular momentum j, and a charge q. We have the differences of the mass between solutions. The delta m is related to the differences between the area of the event horizon, delta a, and also delta j and delta q, where j is the angular momentum and the q is the charge. Omega is angular velocity and phi is the electric potential. So this can be written as delta m equals T delta S plus some work terms, and T is the temperature, S is the entropy. And the second law of the black hole thermodynamics is the Hawking's area theory, which means that the area of a black hole event horizon can never decrease. So we have delta A is greater or equals to 0. And the third law of the black hole thermodynamics is that it is impossible for us to reduce the surface gravity kappa to 0 in a finite number of steps. So as we can see, the four laws of the black hole thermodynamics is very similar to the four laws of thermodynamics that we learned in high school. So how can we from black hole thermodynamics to black hole chemistry? In the previous slide, we know that we can write the first law of black hole thermodynamics as delta E equals to T delta S and plus some work terms. But in high school chemistry, we know that the pressure is also a very important variable in the chemical system. So how can we include pressure P and the thermodynamic volume V in the black hole thermodynamics? So the basic idea of the black hole chemistry is consider the black hole thermodynamics with lambda, the cosmological constant. And the main idea is to identify the mass of the black hole as enthalpy instead of energy, and the cosmological constant lambda as the pressure, and its conjugate variable. The conjugate variable of the pressure is defined as the thermodynamic volume. So in conclusion, we have this table. The left-hand side is the black hole thermodynamic quantities. We have enthalpy, temperature, entropy, pressure. And the right-hand side is the black hole mechanic quantities. We have the mass of the black hole, the surface gravity, the horizon area, and the cosmological constant. So this table means that we interpret the M as the enthalpy of the chemical system, and the surface gravity as temperature of the chemical system, and the horizon area as is proportional to the black hole entropy, and the cosmological constant is interpreted as the pressure of the system. So we have the first law. We have the first law here. So delta M equals to T delta S plus V delta P. So after this brief introduction to black hole chemistry, let's see a very simple example, the first and the most important example for the black hole phase transition, the Hawking-Page phase transition. As we know, the Schwarz ADS solution has this expression where f of r is 1 minus 2m over r plus r squared over l squared, where 2m is the horizon radius here, and L is the ADS length scale. And this is a spherically symmetric solution to the Einstein equation. And then we can compute the thermodynamic quantities, use the table in the previous slides. So we have the M of the black hole, and also the entropy of the black hole, and the temperature, the pressure, and the volume of the black hole. They are all related to the horizon radius r plus, and r plus is the largest root of the f of r here. And we can also compute the Gibbs free energy G, which is the enthalpy minus the temperature times the entropy, so it's M minus Ts. And plug in the expression of the mass and also the temperature, the entropy in the previous slides, we can compute the Gibbs free energy of the black hole system. And we can write it as a function of the horizon radius r plus. And we can also know that the r plus is related to the Hawking temperature T. So we can express the Gibbs free energy T as a function of the temperature, so that we can plot the Gibbs free energy versus temperature diagram. So in this diagram, the vertical axis is the Gibbs free energy and the horizontal axis is the temperature. And as we can see, there are 3 lines. The 3 lines are the Gibbs free energy corresponds to the 3 different horizon radius, and we use the horizon radius to characterize the size of the black hole. So the large black hole has the biggest horizon radius, and the small black hole has a small horizon radius. And as we can see, if we decrease the temperature little by little, and after this THP called the Hawking-Page temperature, the the original preferred state is the large black hole, but after this Hawking page temperature, the Gibbs free energy of the radiation becomes lower, so the preferred state is the radiation state. So this means that after this Hawking page temperature, our black hole system becomes the radiation. So there exists a first order phase transition between the large black holes and the radiation. And for the small black hole, it always has a very high Gibbs free energy, so it is not a stable state. So this is the basic idea of the Hawking page transition. And also, we can compute the coexistence line of the large black hole radiation if we find the pressure versus temperature phase diagram. And in the pressure versus temperature phase diagram, we can plot the coexistence line. So the pressure, is a quadratic function of the temperature, and it has no terminate, has no end point. So it is very similar to what we learned in the solid-liquid phase transition. So we can kind of make an analogy that large black hole is liquid and the radiation is solid phase. So this is just an analogy between the chemical system and the black hole system. And then, after talking the black hole phase transition, there are more chemical phenomena in the black hole system. The most famous one is the black hole triple point. Just like water, in chemistry, we have water. It has the liquid, the solid, and also the gas phase. And we have the triple points of water, where the three phases meet together. And for black hole, we also have the triple point. The triple point is defined as a point where the three phases coexist. And there are many papers study the black hole triple points. And in these three papers, the multi-spinning higher dimensional black holes and also the black holes with higher curvature corrections, they can all have the black hole triple points. And these are the references for these studies. So back to our topic today, can we go beyond the black hole triple point? So we want to study the black hole quadruple point or quintuple points. So these are more complicated ones. And the black hole quadruple points was first found in this paper. So let's talk about the setup of the system. We consider the four-dimensional Einstein gravity coupling nonlinear electron dynamics, and the action of our theory reads like this, where G is the determinant of the metric tensor, and R is the Ricci scalar, lambda is the cosmological constant, and alpha i's are some coupling constants, and F squared is F mu. F mu is the electromagnetic field tensor. So as we can see, if we just has alpha 1, it can be reduced to the Einstein-Maxwell case. And so here we have the higher order terms of this field tensor F. So by varying the action, we can get the Einstein-Maxwell equations. It is a generalized Einstein-Maxwell equations, where the G mu is the Einstein tensor, and the LEM is the Lagrangian for this electromagnetic part. So if we have the field equations, how do we solve it? We can assume some metric ansatz and then some series of the coefficients U. So we make an ansatz that is the spherically symmetric static black holes. So we have minus U dt squared plus 1 over U dr squared plus the spherically symmetric part. And A is the for potential in this case. So after making these metric answers, we can get the simplified field equations here. And if we make the power series of the phi and u here, we can find the coefficients in front of the r. We can find the bi's and also the ci's by solving this field equation here. So we get C1 is minus 2m. It is a threshold horizon radius. And also we have Ci, which is in terms of the bi minus 1 here. And the Q is the integration constant. It is a charge. And we also have the B5, B9, and so on. So we get the coefficients by solving these field equations here. So here, let's consider a simple case. We focus on a setting in which the alphas are non-zero and independent for I is less or equal than 7. So we have the solution here. Phi has this expression and U has this expression. So, and we can also check that if we have only alpha 1, so alpha I are said to be 0 if I is greater than 1, we can recover the Einstein-Maxwell case, which means that the electric potential is Q minus R, Q over R, and the U is just very like the charged black hole, but with this ADS length scale term. So after get the black hole solution, we can compute the thermodynamic quantities of the black hole solutions. So we have entropy here. S is proportional to the area of the event horizon. So we have the entropy is equal to pi times the R plus squared, where R plus is the horizon radius. And we can also get the pressure. The pressure is related to the cosmological constant. And for the ADS case, it is related to the ADS length scale L. So we have P is equal to the 3 over 8 pi L squared. And we can also compute the volume by computing the conjugate variable of the thermodynamic pressure. So we have the volume is equal to 4 pi times R cubed over 3. And also we can find the temperature. It is the Hawking temperature. We can compute it by avoid the cortical singularity. So we have the Hawking temperature here. And also we can find the equation of state. The pressure, there is a formula that related the pressure and the temperature. So it is very like the equation of state, in the chemical system, like PV equals nRT. So this is an analogy of that. So this is the equation of state for black hole. So now let's talk about the quadruple points in black hole phase transitions. After getting that the thermodynamic quantities we seen before, we can compute the Gibbs free energy by computing the mass of the black hole minus the temperature times the entropy of the black hole. And we can also plot the Gibbs free energy versus temperature diagram, just like before. And as we can see, in this diagram, there are 4 stable phases, the 4 blue line, and the 3 unstable phases, the 3 red dashed line here. And we can also see that if we just lower the temperature from here, if we lower the temperature, originally the preferred state is the largest black hole, because the largest black hole has the lowest Gibbs free energy. But when we decrease the temperature, at this point, there is a first order phase transition from the largest black hole to the large black hole here. And also, at this point, we can also observe a phase transition from the large black hole to the small black hole. So, and also at this point, we can observe the phase transition from the small black hole to the smallest black hole. So, in the Gibbs free energy diagram, we can easily see the black hole phase transition. So what are the quadruple points? Can we see in the diagram? So let's look at the feature of the diagram. There are 3 swallowtails, and there are 4 phases. But if I change the parameter, the temperature, the pressure of the system, the locations of these 3 swallowtails will change, and we can make the 3 points meet at 1 point. So this is a diagram. And if we choose these parameters, this specific pressure and also the charge here, and also the coefficients here, if we choose these specific parameters, we can make the 3 points meet together. So the three swallowtails meet together, so we get these points. It is the intersection of all the 4 phases. So as we can see, in this Gibbs free energy diagram with these specific parameters, we can find that if we just focus on a specific temperature, for example, a temperature here, as we can see, one temperature can correspond to 4 blue lines. So this means that at this specific temperature, the 4 phases, the 4 blue lines can coexist. So this is called a quadruple point. So the intersection here, the intersection of these blue lines is called the quadruple point. So the quadruple point is where the 4 phases meet together, where the 4 phases can coexist. And also we can plot the temperature versus horizon radius diagram to better understanding the quadruple points. So in the left-hand side, in this diagram, as we can see, if we have from this temperature range from here to here, we can find the 4 phases coexist. And in this diagram, we can also see that if we have one temperature, it can correspond to different horizon radius. So this means that at one temperature, we can find different sizes of black holes. So this means that for these quadruple points, we have 3 swallowtails, and we have 3 pairs of local extremo in this diagram. And also, we can also find quintuple points and also higher order points. So for generally n-tuple critical points can correspond to n-1 swallowtails in this diagram, and also can correspond to n-1 pairs of local extremo in this diagram. And from now on, let's talk about the quadruple points in the black hole phase transitions. So we have the offshore Gibbs free energy here. In the previous slides, I mainly talk about the onshore Gibbs free energy. And from now on, let's talk about the offshore Gibbs free energy. The offshore Gibbs free energy means that for the temperature T here, it is not necessary to be the Hawking temperature. It is just some ensemble temperature that we set before. So it is some constants that we set to the system. So the offshore Gibbs free energy is equal to the m minus TES, where TE is the ensemble temperature. So we can get the expression of the offshore Gibbs free energy here. And also the TE is our input. So numerically, we can input some value TE here to plot the Gibbs free energy diagram. And in this offshore Gibbs free energy diagram, it is the offshore Gibbs free energy versus the horizon radius R+. And if we choose some ensemble temperature, for example, the ensemble temperature here, we can find that there are 4 local minimum RSS, RS, RL, and also RLL. The RSS is the smallest black hole, and the RS is a small black hole. RL is a large black hole, and RL is the largest black hole. And there are also 3 local maximum. And the local maximum in the offshore Gibbs free energy diagram means that there are 3 unstable phases. And the 4 local minimum here is the 4 stable phases. And all the other points on this curve are some transient states. So for the stable phases, we just focus on the RSS, RS, RL, and the RLL. And we can also see that in this specific ensemble temperature, we can find that the 4 stable phases share the same value of the Gibbs field energy. So this is the structure of the offshore Gibbs field energy diagram. And now let's talk about the offshore Gibbs field energy at some different ensemble temperatures. So the black one is the intermediate temperature, as we've seen before. And if I lower the temperature, if I lower the ensemble temperature, it becomes the blue curve. And if I raise the ensemble temperature, it becomes the red curve. So as we can see, only in this ensemble temperature, the 4 stable phases share the same Gibbs free energy value. But if we just lower the Gibbs free energy, if we just lower the ensemble temperature, the smallest black hole has the lowest Gibbs free energy, and the largest black hole has the highest Gibbs free energy. And also, if I raise the ensemble temperature, as we can see, the smallest black hole has the highest Gibbs free energy, and the largest black hole has the smallest Gibbs free energy, which means that here, for the red one, the largest black hole is the most stable one, and the smallest black hole is the less stable one. And but they share the same structure, that they all have 4 local minimum, means 4 stable phases, and 3 maximum, means 3 unstable phases. And if I put them all together in one diagram, it becomes this. So in this diagram, we can easily see how the Gibbs field energy will change when I change the ensemble temperature. So now let's talk about the dynamic processes at the quadruple point. The black hole phase transition process are described by the Smolov-Chomsky equation, and the Smolov-Chomsky equation is just the diffusion equation under some certain potential, and the Gibbs field energy G here act as a potential in this diffusion process, and rho of T R here is the probability that the black hole system will stay in the size that has the black hole radius R at time t, and the D here is the diffusion coefficient, and the beta is the inverse temperature. So by solving the Smolov-Chomsky equation, we can solve it for the time evolution of the probability distribution zone. And to solve this equation numerically, first we need to set some initial conditions and also boundary conditions. For the initial conditions, we assume that our initial state to be picked at one of the 4 stable phases. Like for example, it can be picked at the RSS or RS or RL or RLL. So we assume that our initial state is to be picked at one of these stable phases, and it is a Gaussian wave pocket. So we assume the initial state to be some Gaussian wave pocket and has the expression here. This is a Gaussian wave pocket. And also for the boundary conditions, since we work in the ADS, the asymptotic ADS case, and in the Gibbs free energy diagram, as we can see, if the horizon radius is lower enough or higher enough, the Gibbs free energy will become infinity. So it is reasonable to set the reflective boundary conditions at the left-hand side and the right-hand side. So we set the reflective boundary conditions at the two ends. So this is our reflective boundary conditions, which means that the current vanishes. So after solving the Smolov-Chomsky and also set the initial and boundary conditions, we can find the time evolution of the probability distribution, though at some temperature. So here, first, I worked on at the intermediate temperature, this case, the black curve. So the first one, that I assume the initial state is the largest black hole. So initially, it is a Gaussian wave pocket peaked at the largest horizon radius. And as we can see, as time goes by, the probability of this largest black hole phase will decreases. So the peak decreases as time goes by. And also, if we focus on the other three horizon radius, the other three stable phases, the largest black hole, the small black hole, and the smallest black hole, as we can see, the probability of the largest black hole leak to the other three states. So the probability of the other three states will gradually increase, and also increase here. So this means that the probability of the initial state can leak to the other three stable phases. And as we can see, after a sufficiently long time, like the time here, the four stable phases share the same phylostationary probability, which means that the black hole phase transition can indeed happen. And after a sufficiently long time, this initial largest black hole state will become the four stable phases coexist together. So this is the meaning of this time evolution of the probability distribution function. And also, if we assume the initial state is a large black hole, so it is a Gaussian wave pocket peaked at here. And as time goes by, we could say that the probability of the initial large black hole will decreases to the other three states, decrease to the largest black hole and the small black hole and also the smallest black hole. And after a sufficiently long time, this probability distribution will become stationary. And for the four stable phases, they all share the same probability. And also for the initial small black hole and the initial smallest black hole. So for the initial small black hole, it is peaked at the small black hole initially, but it will also leak probability to the other three states. And we can also see a little peak for the smallest black hole. This is because the small black hole and the smallest black hole are very close to each other. So we could say a little peak for the smallest black hole here. And also for the initial state is the smallest black hole case. There is a little peak in the small black hole here. Now, let's focus on a two-dimensional diagram other than the three-dimensional one. We just focus on the probability of the four stable phases. So we get the four curves here. The purple one is the largest black hole, and the orange one is a large black hole. The red one is a small black hole, and the blue one is the smallest black hole. So this is just the two-dimensional version of the previous time evolution of the probability distribution function. As we can see, no matter of the initial state, the four cases, after a sufficiently long time here, they all share, the four phases all share the identical phylostationary probability. This means that at the quadruple point, we have the four phases coexist together. And so finally, the spacetime is a superposition of the four stable phases. And then let's talk about the first passage events. For the first passage events, first let's talk about the definition of the first passage time. The first passage time for a given initial state is defined as the required time to first climb to the top of the nearby of the free energy barrier that corresponds to the unstable phases. So in this diagram, for example, the first passage time for a given initial largest phase, so it means that the first passage time for this one is the time required to first climb to RM3 here. So this is the nearest unstable phases from the RLL. So this is the first passage time. And to compute the first passage time, we need to set some observing boundary conditions at the 3 unstable phases, which means that it can across the maximal here. So after some calculations, we can find the first passage time distribution for any given initial phases. So we have the four first passage time for the 4 initial states. And also we can plot the first passage time distribution as a function of the time. So this is the first passage time distribution diagram in this intermediate temperature. So at this temperature, as we can see, in all the diagrams, there is a peak for these curves. And the location of the peak means that at this time, it will have the highest probability to finish the first passage event. So we can use the location of the peak, the characteristic time here, to mean the first passage event. So as we can see, for these 4 diagrams, this one is the initial largest black hole, and this is the initial large black hole, and this is the initial small black hole, and this is the initial smallest black hole. So from the largest black hole first passage time to the smallest black hole first passage time, as we can see, the characteristic time become lower and lower. So the time here is very large, and the time for the large black hole is smaller than this. And also for the initial small black hole, the time here is lower than these two. And also this is the smallest one. So this means that it is easier to finish the first passage event for the smallest black hole, and for the initial largest black hole, it will need more time to across this maximal. So this means that the first passage time can capture the structure of the Gibbs free energy barrier here. So this is the first passage time distribution for different ensemble temperatures. Originally, we have this Gibbs free energy diagram for different ensemble temperatures, and we can also find how the first passage time is related to a different ensemble temperature. Let's take the largest black hole, for example. For the largest black hole as the initial state, so our initial state is here or here or here for different temperatures. So at figure A, it has the smallest temperature, and the figure B has the intermediate temperature, and the figure C has the highest temperature. So as we can see, as temperature increases from A to C, the peak time becomes larger and larger. So this means that for the highest temperature case, the first passage time for the largest black hole is the highest one. This means that for the largest black hole at high temperature, it is harder to cross this barrier. And for the low temperature one, the largest black hole is very easy to overcome this barrier here. So this is the physical meaning of the first passage time distribution. Now let's see the probability evolution for the four stable phases at a low temperature. So these are the two-dimensional diagram. Instead of the three-dimensional one, it is easy for us to say, to focus on the four stable phases. So for the initial largest black hole case, the first diagram, as we can see, the probability will leak very suddenly, and also the three states, the probability of the three other states will gradually increases. So in this diagram, as we can see, the orange one, the large black hole, will first increases. So this means that at low temperature, for the large black hole, it has the shorter first passage time here. And after sufficiently long time, as we can see, the four stable phases are all reach a stationary case. So it becomes stationary, but it is different from the intermediate temperature one. The four stable phases has different probability distribution. So the blue one, the smallest black hole, has the highest probability, and the largest one, the purple curve, has the lowest probability. So this means that for the smallest black hole, it is the most stable black hole. So it is consistent with the offshore Gibbs field energy diagram here. So in this temperature, the smallest black hole has the lowest Gibbs field energy. So that's why the probability of the smallest black hole is the highest one here. And also for the initial large black hole, the orange probability will decreases, and the other three phases will increases. And the first one is the red one, is a small black hole, and it is also consistent with the lowest first passage time here. And after sufficiently long time, as we can see, this is the same as this one, and they are all determined by the structure of the Gibbs field energy here. And also, for the small black hole and the smallest black hole, we observe the similar situation. For the small black hole, it will decreases, and because the smallest black hole and the small black hole are very close to each other, so the blue one will have a peak here. And also, it is the same case here. And also have after sufficiently long time, they will reach stationary, which is determined just by the structure of the Gibbs field energy here. And let's see the probability evolution for the four stable phases at high temperature. This is the offshore Gibbs field energy for the high temperature one. For the high temperature, the most stable phases is the largest black hole, and the smallest black hole has the highest Gibbs field energy. So if we assume our initial state is at the largest black hole here, so it will always dominate the probability, and there are very, very small probability linked to the other three states here. But for the initial large black hole, the orange one, as we can see, finally, the purple one, the largest black hole, will dominate. And the other three are the probability for the other three phases are very small. Also for the small black hole and the smallest black hole, finally the purple one, the largest black hole will dominate. So now let's make a conclusion. So initially the probabilities will leak to the other three states. This means that the black hole phase transition process can indeed happen, and the early time behaviors depends on the first passage time. And finally, the probability distribution will become stationary, and we have the probability for the four stable phases is just determined by the structure of the Gibbs free energy. And this is the references. You can learn more about the black hole chemistry and black hole phase transition by looking at these references. And also, we would like to thank Jerry Wu, Sijiang Yang, Shao Wenwei, Yu Xiaoliu, Wang Yongqiang, and Lia Afsholi for helpful discussions. Thank you for your attention. If you have any questions, please free to ask.是在腾讯会议吗？哎，我好像没看见，不好意思，是在哪？嗯，哦，我看到了，不好意思，不好意思。第一个问题是大黑洞向小黑洞的相变在现实中可以被观测到吗？就是现实中我们可以观测到某个黑洞世界突然变小。对于第一个问题，目前为止好像还没有任何的实验证据可以观测到这个黑洞相变的过程。但其实这是一个非常新的 idea， 它是标志着这个我们的 space-time 可以看作是某种 superposition 的这种概念，因为在那个就是临界点，它可以看作是大小黑洞的一个 superposition， 但是对于这个相变的实验好像是并没有证据的，所以这个问题是没有被现实观测到。然后第二个问题是研究单个黑洞解的热力学函数，那么几种态共存在的物理上是什么意思？就像说，对这个问题其实就是可以用superposition of space-time 来解释，就是我们确实是研究某一个单一的黑洞解，但这个单一的黑洞解它的 horizon radius 可能解出来可能有好几个，然后我们通过研究这个 black hole phase transition 的过程，就可以研究它们在这几种大小的 black hole 之间的转换，然后在这个triple point or the quadruple point 可以认为是它们几个black hole size 的一个 superposition，是这样的一个物理图像。Sorry for this. Sorry, could you repeat? The question is very hard to answer because I didn't see any experiments for these black hole phase transitions, but maybe in the future, we may observe the black hole phase transition. Yeah, right. Yeah, thank you.